right? No. No, that quiz was just, I want to keep everybody honest here, okay? I expect that, you would do the homework and that you would understand what you're doing. And that if I gave you a quiz on 2 homework problems that you'd be able to successfully complete that in class. I think that's more than fair. You could disagree with me. But if we covered it last class, I expect you to do the homework, have it completed, and be prepared the next class. That's the expectation. If you keep putting it off and I'll find time and I'll get it together before the exam, it's going to be a difficult road for you here, all right? You always have to stay on track in a class like this, all right? So I'll see how they were and talk about it next time. All right, so let's get going. We were talking about continuity last time, and the graphical meaning of continuity, make sure I'm recording, okay, is that you can basically draw your function without picking up your pencil. That was the idea behind continuity. And I told you that all polynomial functions, rational functions, trig functions, and exponential log functions, all of them are continuous on their domains. And that's kind of where we had finished up. I didn't get to talk about composition of functions, which says that if you have 2 functions that are continuous and you do functional composition, that's f of g of x or g of f of x, this is a college algebra thing, that you will still remain continuous if you compose 2 functions. So I have some examples here to look at. The first one, I don't know if you can see that. Let me make this a little bigger for you. If you look at the function sine of x squared minus x squared minus x by itself is a polynomial, so it's continuous. And then the sine function is also a continuous function. So if you plug this continuous polynomial into a continuous function, this is the result. And you can see that that is a continuous function still. And that works for all composition. So here's another example, e raised to the cosine x. So cosine x by itself is continuous, and then e to something that's exponential, that's continuous. So when you compose the 2, you get this blue curve, it's also continuous. All right, and I can continue with more and more examples. All of those can be drawn without picking up your pencil. Well, not this one, but it's okay because the part that's cut off in this picture is part of the function where the domain is restricted. So on the implied domain, for the values of x which you can plug into this function, in here it's nice and continuous. The fact that there's nothing here is okay, because these numbers can't be plugged into the function. So that's the next little idea. And then we have this intermediate value theorem. This is really actually a very important theorem in mathematics. And it says that if you have a continuous function on a closed interval a, b, where your function is not equal to itself at the 2 endpoints, then let n be any number between f of a and f of b. There exists a number c in the interval ab such that f of c equals n. What? Okay, so here's what that theorem is saying. Let's say you have a continuous function, all right? So here's a continuous function. Everyone agree? Okay, let's restrict the domain to a closed interval. All right, so now let's stop it at some point A and some point B. So come down here, this is like B. Up here, this is like A. So do you agree that we have a continuous function on a closed interval? All right, this theorem says that we need to check to make sure that the 2 endpoints are not the same. So the 2 endpoints aren't the same, right? Down here, you're getting -12. Up here, you're getting 13. So they're not the same. Then let's choose any number we want between those 2 values of 13. So up here at 13, I can choose any value between there and down here, -12. So you tell me when. I'll stop. Ready? Whenever you want. Yeah. Right there? Okay, there we go. 10.3. All right? This theorem says that guaranteed, there must be some matching point on my graph that comes from some point C, right? So there's some point C between A and B that's going to achieve that value of 10.3. This only works for continuous functions on closed intervals. So let me go back. If I changed that value of n, you can see that I'm going to find somewhere on the function an x value, right? I'm going to find somewhere where I'm going to get that output from the function. And that works for any number between the two endpoints. Make sense? Okay. So that's the intermediate value theorem. Here's an example of a function that would not satisfy the intermediate value theorem. So watch me do the same thing. I restrict it to a closed interval. I make sure the two endpoints are different. They are, right? And then I try and choose a value of n in between. So do you notice that right here, if I choose this value of n, I'm going to have somewhere on the graph where I'm getting that output, yes? But if I come in here, something happens there. Here, there's no function, there's no value that's going to, no output of the function that's ever going to achieve that n, right? So why did the intermediate value theorem break down here? Because it wasn't a continuous function. This function failed to be continuous because what type of, this was almost a quiz question. I was going to ask you to identify the 3 types of discontinuities. So what are the 3 types of discontinuities? Jump, removable, infinite. Those are the 3. So this would be an example of a jump discontinuity. So therefore, the intermediate value theorem does not apply. All right? All right, now here's a way we can use the intermediate value theorem. Look at this equation right here, cosine x equals x. If you were asked to solve that equation by hand, right, so solve for x, this would be extremely difficult to do. In fact, it cannot be done algebraically. There's no way to solve for x here. Can't do it. I mean, you could say it's already solved for x, but the problem is x is over there too. So in order to know x, you have to know x, and it's circular here, right? So maybe you try and come in with arc cosine on both sides. That way you can free this up. But if you do that, you trap this x inside an arc cosine. So there's no algebraic way to isolate x here. But the question here is, can we use the intermediate value theorem, the theorem I just showed you, to show that it has a solution? I'm not asking you what the solution is, but can you use that theorem to show me it must have a solution in this interval 0, 1? Okay? So let's think about this. If I were to try and visualize this function, if I plug 0 in, right? You know what? Let's do it this way. Let me get that little mouse out of here. Am I not on? What's going on here? There we go. Okay, so let's do this. I'm trying to solve this equation, right? Everyone with me? Okay, so what I'm going to do first is I'm going to rewrite this equation like this. You all agree that's the same equation? Okay. Now, on the left side of the equation, I'm going to call this piece right here f of x. So this by itself is a function. Are y'all okay with that? That's a function. When someone asks you to set a function equal to 0, what are they actually asking you to find? The roots, right? The x-intercepts, right? Yes? So if I call f this function, then this equation means find me the x-intercepts of this, right? Okay. I'm trying to show you that there's at least one x-intercept in this interval 0, 1. Make sense? So let's try and just plug 0 into the function. What's f of 0? So look at this function. What's f of 0? Cosine of 0 is 1 minus 0. It's 1. So we get 1. Okay. What's f of 1? So what I'm doing is I'm doing these two endpoints, and I'm trying to see what's happening. What's f of 1? Cosine of 1 minus 1. Ooh, what's cosine of 1? If you were stranded on an island and you didn't have a calculator.
Well, you said cosine of x equals x, so that means cosine of 1 equals 1.
What do you mean?
It was a bad joke.
I didn't get it. I'm sorry.
Math humor.
What is cosine of 1? Okay, let's go back to our cosine function real quick. Let me just graph it. Here's cosine x, right? That's cosine x. Okay, where is that happening? Where's that happening? Where's that happening? Where's that happening? So what is halfway? Pi, right? This is pi over 2. Sorry, 2 pi. This one right here is pi over 2. Okay? So I'm asking you to plug 1 into this function. Cosine of 1 and then minus 1, right? That's what we want? Cosine of 1. Where's 1 on this number line? Okay, is it bigger or smaller than this number? Smaller. That pi is 3.14, right? 5, whatever. Keeps going. Okay, what's half a pi? Well, that's 3.1415 divided by 2. That's still bigger than 1, isn't it? Yeah. So shouldn't it be somewhere over here? So 1 is somewhere in here, right? And if I plug that in, I get some value here, don't I? Isn't that number smaller than 1? Yes? So would you agree that this number is smaller than 1? And if I subtract 1, my answer must be negative. Agreed? So even though I don't know this, let me go back. I wanted to plot this. When I plugged in 0, we got 1, right? So when I plugged in 0, we got 1. Okay? And when I plugged in 1, what did we get? Some negative number, right? So I'm talking about this graph right here. All right? I only use that graph, right, to figure out that that number is smaller than 1, okay? So, what? What does this mean? Does this graph have an x-intercept between 0 and 1? Does it?
No.
Look, here's the graph, right? I don't have the whole picture, but here's what I do know. Starts here and ends here, right? And I have to draw it without picking up my pencil. Why?
Because it's continuous.
That's continuous, and that's continuous. And when you subtract two continuous functions, it's still continuous, which means it must go through there somewhere. I don't know where it goes through, though. See? I don't know. But I know that it has to get from here to here, right? And that means it has to cross. And that means it has to have a solution. I don't know what the solution is. Right? I don't. Understand this? That may not impress you, okay? Because we still don't have an answer, do we? Right? We still don't have an answer. But here's the way we could actually get an answer, at least an approximation. What if now, if I know the answer is between here and here, what if I instead look between 0.5 and 1/2 and 1. Okay, so what I'm doing is I'm cutting this up into two pieces. What if I look between 0.5, I plug in 0, I get 1, I plug in 1/2, and I wind up getting a positive number, then I know that it did not go through the x-axis there, right? But if I plugged in 1/2 and got positive and plugged in 1 and got negative, I know it went through somewhere here, don't I? So then what I could do is I could eliminate this, and I could take this one and break that one down to be something like 1/2 to 3/4, and then 3/4 to 1. So what I'm doing is I'm cutting this one in half, and I'm looking, where is it switching? Does that make sense? And what I can do is keep on cutting it and cutting it and cutting it, and then just do that over and over and over and over. This is exactly the way a computer solves an equation. It uses this idea. This is actually called, there's a math course called numerical analysis that teaches you how we use computers to solve equations. And this is the first method you ever learn. It's called the bisection method. And now there are other methods that we will actually study later in this class called Newton's method, which is going to give us the same result, but it's going to get us there faster. So with computers, it's all about number of operations that it takes to get to a solution. So this method will get to a solution, but it takes the computer a lot of operations to actually get to it. Whereas you have a different method, it's going to get there faster. So anyway, do y'all kind of see what's going on here?
Yes, it's halving and halving.
It's halving and halving, and every time it goes into half, it checks each one.
Yeah, you remove one.
It says, do I have a change in sign? Do I go from positive to negative here? If I do, then I'm going to half that. If I don't, I'm going to go look at this one. And then, and then just keeps on refining it. And what happens is you know, your answer in your computer will give you an answer, whatever it is. I don't even know what the answer is, but it'll give you a decimal, like 1 point blah, 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 blah. And the way it's getting that answer is it gets it down to an interval that's so small that it just takes the measurement of that interval, the distance, and says that's the answer. Or it'll take like the midway point. So at some point your computer says, all right, I'm done. I'm going to stop halving these, because it could half forever. But there's a certain tolerance that's built into the program that says, look, as soon as the length of this interval is like 0.00000001, then you're done, okay? All right. So the intermediate value theorem on its surface does not look very powerful, because all it does is guarantees the existence of a solution. But if you incorporate that theorem along with a computer, you can do some very impressive things. Okay, let's go. Now we need to do some examples. We're still talking about continuity right now, all right? Continuity. So I'm going to give you a function here. This is a piecewise function. Means it's two different functions on two different parts of its domain. And I'm going to say that it's this function if x is less than or equal to 1, and this function if x is greater than 1. Now, I have not presented you with the question yet, right? I just want you to think about this function for a moment. And I want you to think about it in terms of its continuity, whether or not it's continuous. Can you draw it without picking up your pencil or not? Well, if our function was just the top one, is that continuous? Yes, it's a polynomial. The bottom one, is it continuous? Yes? So really, there's only one place that we could actually have a problem. And where would that be? At what x value would we potentially have a problem? At 1. And that's because to the left of 1, I'm this, right? And to the right of 1, I'm this. So graphically speaking, here's 1. To the left of 1, I'm this parabola, right? I don't even know what it looks like. I do know it opens up, right? So, you know, it looks like that, whatever. Yes? That's continuous. And at 1, if I plug 1 in, if I actually ask you what's f of 1, do you plug it into the top or the bottom? Top one, because of that equal sign. So f of 1, what is f of 1? 5. So I know that at 1, I have a dot here at 5, and then it's a parabola, right, to the left? And now to the right of 1, I'm this, which is another polynomial. It's cubic, right? Cubics do this or this, right? And because it's a negative in front, it's going to do which one? This one right here. Okay, so it's going to do this. So I do know that this side goes down. And I don't know what happens here. It comes in here. It might squiggle a little bit. But here's the thing. I don't know if it actually meets up with that point. It might do this and then go like that. Or it might be above it or way down here or right on top of it. What I would like to have is for it right on top of it. And then it would be continuous, wouldn't it? So the question is this function continuous at 1? Because we know it's continuous everywhere else.
No, it's not.
Okay, well, let's see why, all right? Is f continuous at 1? Question mark. Now, you may just be able to kind of investigate it and look and see it's not going to work. But we need to use the precise definition of continuity. So let me put the definition of continuity up here so that everyone's on the same page. And I'm going to leave it up here. A function f is said to be continuous at x equals a if the limit as x approaches a of f of x equals f of a. And that's the one you need to remember. That's the formula you need to actually hardwire, I guess. And it seems like maybe that looks weird to you, but let's just go through it and try and make sense out of what it's saying. Everyone have it down? Okay. In order for a function to be continuous at a point A, here's what we need to have happen. First of all, that limit has to exist. That means as we approach A from both sides, our function needs to be going somewhere. Right? So that means this. Here's A. I've got my function coming in from the left and from the right. Do you agree that the limit here exists at A? Yes? Okay. Because the left and the right go the same place. I need that limit to be equal to this. Now this is your college algebra. Just equal to the function's value at A. Which means that you need this little circle right here to be filled in with a solid dot. And that way your limit is actually going to the point that the function is defined to be. If this holds true, then obviously I can draw it without picking up my pencil. Make sense? Question?
Saying if it's not closed, then it isn't continuous?
That's right. See, if this, think about it this way. Let's say it was defined this like this. This function would not be continuous at A. And the reason why is because even though the limit exists, right? And the function is defined at A, they're not the same. See, they have to be the same in order for it to work. So here, yes, f of A is a number. The limit exists. I can even illustrate it this way. Let's call this L and let's call this M. F of A is M, right? The limit is L. L and M aren't the same thing. Okay? So we need this to hold for something to be continuous at A. Y'all follow that? Okay, let's go back over here and look at this question right here. Is f continuous at 1? Well, we need then the limit as x approaches what? What do we need to show is true? As limit as x approaches 1 of the function, right, needs to be f of 1. Okay? That's what we need to happen in order for us to say it's continuous. And on a test or on a quiz in the future, if I give you a problem like this and I ask you if it's continuous at 1, this is the type of thing I need to see. Not just yes or no answer without any work. Okay? You need to show me the definition first and then the work. So let's look at this equation. I'm actually asking myself this question of whether or not that's true, right? It's like, is it true that limit's equal to f of 1? All right, well, let's work with the easier side. And we're going to kind of work with these left and right side and see if they maintain equality. What is f of 1? So you come up here. You already told me to plug in 1 there. It's 5, right? So the right side of this is 5. Still a question mark. What I still don't know is what this limit is, right? I don't know what this limit is. So I'm going to have to do a little bit of scratch work here. All right, this is going to be a little bit of scratch work. From now on, if I do scratch work, I'm just going to say SW, okay? My scratch work is this. I need to figure out what this limit is, right? And when the limit does not have plus or minus on it, it means you have to do it from both sides and see if they match, right? So I'm going to be checking two limits. Limit x approaches 1 from the right of the function, and I'm also going to be doing, after I do that, the limit as x approaches 1 from the left of the function. And it doesn't matter which one you do first. Does everyone understand that we need to look at both of these in order to answer what this is? Yeah. Yes? Because it doesn't indicate left or right, that means it's both. All right, so now, what does this mean? I mean, I'm doing the limit, I'm letting x approach 1 from the right, but what function am I using?
The x squared, you use both of them, right?
Well, it can only be one. Which one am I going to use?
From the positive, you'll use the top one, and from the bottom, you'll use the
What is approaching 1 with the plus sign, what does that mean? Which side of 1 am I on? Right side of 1? So like on a number line, if this is 1, I'm actually over here, right? These numbers that I'm approaching at are bigger than 1, aren't they? If I'm bigger than 1, I'm on this function. See? So I'm going to be here. So what I'm going to do is replace this f of x with the actual function, the piece of the function that I'm on, because I'm bigger than 1. Is that clear? Now, plug in 1, and let's see what we get. So what do you get? 3. Okay. I can already, at this point right now, say that this is not continuous. Why can I say it's not continuous? Yeah, because even if this one came out to be 3, the limit would exist then, right? Because these two would match, but it doesn't match 5. So it's already dead in the water. But I'm going to continue, and I'm going to work this limit out also, all right, just to show you. This limit, as x approaches 1 from the left, this time, if I'm to the left of 1, I'm over here on this side, and that means I'm going to be less than 1, so I'm using this function. So I put x squared plus 4 here, and what is this limit? That's 5, okay? So this is okay, this is actually good, but this one isn't. So what is this limit? Go back to when we were doing limits. What is this limit? Does not exist. This limit does not exist. Because the left and right limits are not the same. And therefore, obviously, does not exist is not equal to 5, right? So these are not equal. Therefore, is it continuous at 1? No. Understand? You sure? I'm going to do another one. What if this was 3, and what if this one would have come out to be 3 also? Still would have been wrong, because then this side would have been 3, and it would not have been equal to 5, and you would still have no continuity. So, okay? Change the problem. How about this one? F of x is x squared minus 16 over 4 minus x if x is not equal to 4. And then negative 4 plus minus x if x is equal to 4. This one's a little more in depth, I guess, a little more thinking here going on. So where do you think is the only place I would be concerned about continuity? At x equals 4. Now let's make sure we understand why. If x is not 4, right? If x is not 4, if x is not 4, that means to the left or to the right, yes? Either side of 4. Then we're this function. And what type of function is this? A rational function. And rational functions are continuous on their implied domains. What's the only problem point that we have in the domain of this function? Or that what number is not in the domain? 4, right? But see, we're not 4, right? So this is a perfectly fine continuous function on its implied domain. So I can draw it without picking up my pencil. Okay? What about at 4? At 4, I'm this, right? And this is just a line, isn't it? Now it's kind of weird because it's a line, but it's only defined at one point. Right, x equals 4, so tell me what I get. When I plug in 4, what do I get? -8, right? So -8 down here. So it's just a single point, right? So I have a single point down here, I know that. The question is, does that rational function come into this point or not? Do y'all see what I'm saying? And we don't know. We have to actually do the work. So is f continuous at x equals 4? Question. All right, what do we need? We need what to be true? The limit as x approaches 4 of the function to be equal to f of 4. All right, that's what we need to be true. Let's see if it's true or not. Let's see if it's true or not. Well, let's start with the easier part, which is the right side. What is f of 4? So if I'm plugging in 4, I'm here, right? And we already plugged it in, we get -8. Now we need to figure out what the limit is on the left side. And that requires us breaking it into two limits, one from the left, one from the right. So what is the limit? So this is my scratch work. What is my limit as x approaches 4? Let's go from the left first. And then after we do that, we'll take the limit as x approaches 4 from the right and see what happens. So tell me right now, what happens if I am approaching 4 from the left? Which part of the function am I on? The top one or the bottom one? Top one. Because I'm less than 4, which means I'm not 4, right? So I'm up here. So this is really the limit as x approaches 4 from the left of x squared minus 16 over 4 minus x. And now try direct substitution. And what happens when you do direct substitution in here? You get 0 over 0. And what do you do when you see 0 over 0? You got to do some algebra, right? Or a trick. Do you see the algebra you're going to need here? What's that? I think I heard you. You might be able to get away with the conjugate here, but I think there's a more direct path. Numerator is a difference of squares, right? So let's realize that that's x plus 4 times x minus 4 over 4 minus x. Be real careful here. Now what? Yeah, these almost cancel, right? These two almost cancel. This one is positive x, this one's negative x, this one's negative 4, this is positive 4. These two factors are off by a sign. So I can factor a negative out. So I'll do that. Limit x approaches 4 from the left. I'll factor a negative out of the bottom one. Is that all right with you? Okay, so if I factor a negative 1 out of the bottom, I'm going to be left with negative 4 plus x. So this is algebraically the same expression. And now these two cancel, don't they? They're exactly the same. Try direct substitution again. What happens if I plug 4 in to this over negative 1? What do I get? -8. All right. So this is looking promising now. Because for it to be continuous, right, I needed both limits from the left and the right to be equal to this. And it's -8, and I've got -8 right now. I just need the other one to do the same thing. So let's see. I'm doing the limit here. X is approaching 4 from the right. Which function are we on? Top one or bottom? Top one again, right? Because as long as we're bigger than 4, we're not 4, right? So we're up here. And isn't that going to cause the same problem it just caused a second ago? Like 0 over 0? So why don't I go ahead and just take this right to where I know it's going. This is going to x plus 4 over negative 1 again, because I would do the same exact algebra, right? And then I'd still get what? Negative 8. And therefore, this limit is negative 8. And therefore, it is continuous. So what we actually had, if we graphed this, if you were asked just to graph this function right there, if you were asked to graph that, it would actually look like, here's negative 4. It would look like this line right here. I'm telling you right now, if you were to break your graphing calculator out, type in this function, just this top one, forget all this, just that, it would actually graph this, okay? And what your calculator wouldn't show you is that at 4, you have a hole. Because it's undefined, right? This one would have been undefined at 4. This would be a discontinuity, wouldn't it? But it's a certain type of discontinuity. What type of discontinuity is it? A removable one. So if I redefine the function, and this time instead of just this, I add this piece to it, and say, hey, look, when you get to 4, go ahead and fill that hole in with negative 8, then it's a continuous function. So what I've illustrated here is how you can take some weird rational function like that and remove its hole and maintain the continuity of the function. All right, y'all doing all right? Continuity is a weird topic. It's different. I realize that. We're going to do one more. And this one's going to be a little bit kind of mind-blowing, but you have a homework problem like this, so. Now, while you were taking the quiz, I made this problem up. So let me just get this up here real quick. Thank you. Yes. Did not mean for that to happen. Okay, so here we go. We have this piecewise function. Here we go. Here it is. It is, the top piece is x squared plus 3x minus 4. And this is if x is less than 2. Okay, so nice little parabola if x is less than 2. And then it's ax squared minus bx minus 2 if x is between 2 and 3. And notice I put x is bigger than or equal to 2 or strictly less than 3. And then finally, it's ax plus 5b if x is greater than or equal to 3. Okay. There we go. This is fun. This is fun. You should right away realize that I've put variables within the function that I've not defined for you, right? Like I have put here a x squared and bx, and I put ax in here 5b. See that? I haven't given you numbers. So if I were asking you, just like in a college algebra class, hey, graph that parabola, you would have no problem graphing that, right? Yeah. Well, you could do that, right? Now, if I ask you to graph this one, you couldn't graph it for me because you don't know what a and b are, right? But you know it looks like a parabola. That's about all you know. But if I gave you a and b, you could graph it. Here, this is a line, isn't it? If I give you the number here and the number here, then it's some sort of line. So in this function that I have given us, we know that we have this place where we have something important happening at 2 and at 3, right? So to the left of 2, I'm that parabola up there, right? And it opens up, right? So it goes like this. And when I get to 2, it has a hole. It has a hole because it's not defined there. With me? Then, in the middle, between 2 and 3, it's this parabola. I don't know if it opens up or down, though, do I?
No.
Because it's, I don't know, A and B, right? So let me just kind of guesstimate. Will it be defined at 2? Will it actually have a dot at 2? Yes? So I don't know where it is, though, because I don't know A and B, right? So I'm just going to place it here. And I'm going to just kind of guess that it's opening down right now. And then when I get to 3, it's going to have an open hole, right? And then this one, again, because I don't know A and B, I know at least that it's a line. And is it defined at 3? Yeah, so it's a dot. I don't know where that dot is. And it goes out to the right. To the left of 2, it's continuous. Between 2 and 3, it's continuous. To the right of 3, it's continuous. So what do you think the 2 questions are going to be about? Like the 2 interesting points are going to be, is it continuous at 2 and 3? Right? Is it continuous at 2 and 3? Well, we don't know, right? Because we don't know A and B. Agreed? So that's actually not the question I'm going to ask. The question I'm going to ask is for you to find the A and B that make this continuous. Now, that's difficult to illustrate without some animation, so I made a quick little animation here. Why is it all dark like that? Oh, there we go. It's not fitting. That's as good as I'm going to get it. Okay, so, man, that stupid dot right in the middle of the page. Yeah. It's, okay, I'll just move it like this. Okay, so here's the same picture that I drew over here, all right? But I'm having the computer actually plug in some values of A and B for me. And so what we're trying to figure out is what happens if I change A. Now watch what happens with the shape of these things as I change A. Do you see those things moving around? Okay, and if why does it keep on going to that weird color? Okay, if I change B, it moves them around too. I need to figure out how do I change A and B exactly to make them line up. It's close there, right? Not quite, so maybe just tweak A a little bit. Ah, shit, wait, there, maybe? Okay, so look, a problem like this cannot be done like the first one I gave you. The first one I gave you, you could actually do that problem without even doing any limits. You just kind of played with it. Like, I think you had the answer right away. Like you said, it wasn't continuous. You can't do a problem like that, like this, with some shortcut. You have to go to the definition. Understand? That's the only way we're going to get A and B. So at least understand what we're trying to accomplish here? Yes? Okay, so let me put the actual question up on the board. We're trying to force these things to all come together so we can draw them without picking up our pencil. This is the question, find A and B so that F is continuous everywhere. Now, everywhere may sound like, wow, how am I ever going to do that? But we already know to the left of 2 it's continuous. We already know between 2 and 3 it's continuous. And we know to the right of 3 it's continuous. This really translates into find A and B so that F is continuous at 2 and at 3. Right? That's what we need. So we need 2 things to hold. We need F to be continuous at 2 and F to be continuous at 3. That's what we need. If we can accomplish that, then we are in business. Do you agree? All right, let's make it happen. So let's talk about this first condition. We'll label these condition 1 and condition 2, all right? So let's work on that first condition that we need. For the first condition, we want limit what? as x approaches 2, that's not the definition. You're doing the scratch work right now. Limit as x approaches 2 of what? The function, right? F of x. That needs to be equal to what? F of 2, right? That's what we need. We need that to happen, right? For this to be continuous. Now, let's start trying to work with these again. What is f of 2? So where are we going to be? Top, middle, or bottom function? Middle function, right? Middle function. Can you plug 2 in to this? Yes, and you're plugging it in for which variable? X, right? So what happens if you replace, well, yeah, I think you can do it. What happens if you replace all the x's with 2's? What do you get here? You get 4a minus 2b minus 2. Do you all agree that's what I would get if I plug 2 into the middle function? I still don't know what a and b are. Now, what is the limit as x approaches 2? Now, we're going to do a slight shortcut here. This means technically that we need to do scratch work and approach from both sides, right? From both sides? Now, if I approach 2 from the right of 2, would I be the top, middle, or bottom? Middle, right? And I already know what happens there. It turns into this, doesn't it? The only thing that's interesting to me is what happens from the other side of 2, which would be this one up here. Do you all follow me on that? No? Yes? Okay. Here's 2. We have to approach it from the right and from the left. Yes? If I approach it from the right, I'm going to be on this one. Agreed? If I plug 2 into this, what am I going to get? This right here. Right? Who cares? I already have that. That's okay. The more interesting part is what happens when I come in from the left. If I come in from the left, I'm up here on this one, right? Mm-hmm. And if I plug 2 into here, I get something else, right? So what do I get? What I guess I'm getting at is I'm going to change this to just the limit from the left because this is actually the value of the function at 2, which uses the middle function, which is the same as coming in from the right. So I'm trying to cut down on the amount of work I have to do by only coming in from the side that's different from what's happening on this side.
Mm-hmm. Yeah, you're using the fact that it's equivalent to
exactly.
that function.
Yes, on that piece, yes.
The
other one's not. It's something else, right? Mm-hmm. So I'll just approach the function from the left, which means I'm using the x squared plus 3x minus 4. And now let's plug 2 in here, and what do you get? 6. So I get 6 is equal to 4a minus 2b minus 2. That's what I get, right? Well, you can solve this for a or b, can't you? But the problem is we have 2 unknowns. We have 1 equation and 2 variables. You cannot solve this, right? But system of equations. System of equations is where you have like multiple equations, multiple unknowns. But for a system, you would need another equation, wouldn't you? Where are you going to get the other equation from? This was only the first condition. The second condition is going to generate a second equation. And then we're going to have 2 unknowns and 2 equations, and we'll be able to solve. So there's a lot going on here. All right? You good with this so far? I'm just going to leave this. I'll come back to it in a second because I don't know what a and b are yet. Go to condition 2. What do we need to happen? What do we want to happen here for condition 2 to be met? Limit x approaches 3 of the function needs to be f of 3. Okay. That's what we want to happen. Let's start with f of 3. Where do we plug in if we're going to try and plug 3 into this function? The bottom one. And we're placing the x with 3. So the right side of this becomes 3a, right? Plus 5b. And now this limit that I'm about to take here, which side of 3 should I go after? So the bottom function I just used, didn't I? And that was greater than or equal to 3. So I should use the function that's on the other side of 3 which would be this one, right?
Yep.
So that should be the left-hand limit. So I should do the left-hand limit of ax squared minus bx minus 2. And then do a direct substitution of 3 into this. And what would happen if you put 3 in here? 9a, because you're squaring 3, 9, minus 3b minus 2 equals 3a plus 5b. Bam. We have a second equation with two variables in it. Any questions on how I got this? Are you feeling nauseous? How do you feel? I'm not done, right? I'm not done? Okay, so now let's clean this up just a little bit. Let's take this first equation and let's get all our a's and b's on one side and our numbers on the other. So I'm going to leave 4a here minus 2b here. I'm going to add 2 to both sides. So it'll look like 4a minus 2b equals 8. Y'all agree? That's our first equation, so check, I've used that one. Let's get all our a's and b's on the same side here. So I'm going to move the a's and b's to the left. So I'm going to subtract 3a. That should give me 6a. How about my b's? I have a minus 3b here. I'm going to take this 5b and bring it to the other side, so subtract it, so I get minus 8b. Y'all still there? Equals, now let's get all the constants to the right side. So 2. And this is my system of equations. So in college algebra, we learn how to solve systems of equations. There's 2 common techniques to do it. They're called substitution or elimination. And it's up to you as to how you want to go about this. So any preference here? Eliminate. How many of you like elimination on this problem? Why are you so shy? How about substitution? How about everyone else? Don't know what it's called? So look, let me just describe the difference between the two. And hopefully you'll remember this. Substitution means you take one of these equations and you solve it for either one of the variables. So like you solve this for A or you solve it for B, then you take that answer and plug it in here. And then you can solve. And that's called substitution. Elimination, what you try and do is add these things down vertically and get one of the variables to go away. And right now, if we add down, nothing goes away. We get 10a and negative 10b and 10. That doesn't work, right? Does that sound familiar, those 2 methods? Now, if I were doing this problem, I would do elimination. And the reason I would do elimination is because I'm looking at this and I can see a very easy way to kill off the b's. Now, if you like substitution, I trust, that's why 1414 is a prerequisite for this class. I trust that you could do this with substitution. But elimination, what I would do is multiply the top equation by negative 4. Now, why do I do that? Because it'll distribute through, and I get a new system that looks like negative 16a, what?
Negative 16a with positive 8b.
Plus 8b equals negative 32. Now, rewrite the other equation. And you see what I did is I achieved my goal, which is to get the b's to cancel on when I add down now. So if I add these 2 down, straight down now, I get negative 10a. The b's cancel, and here I get negative 30. And now I can divide both sides by negative 10. I have a just like that. A is 3. Okay, now once I have A, how do I get B? I can go into either one of these equations. It doesn't matter which one. I just pick one and I just replace A with 3. So I'll just grab this first equation and I'll replace A with 3. So 4 times 3 minus 2B equals 8. So 12 minus 2B equals 8. And I trust that you could solve that. I think B is 2. Yes?
What test doesn't matter how we get those values?
Which method?
Yeah, because you could use the matrix on
You could, yes, you could use your,
the, like, are we allowed to do that?
Your-
That's for sure.
the question that's being presented is, there is a way to solve systems of linear equations using your calculator. What do y'all think? I think for this, I would like to see the work. Now, if we ever get systems of equations that are 3 equations, 3 unknowns, I would be okay with that. But with a 2 and 2 like this, 2 equations, 2 unknowns, I think everyone just kind of needs to know how to do it. It didn't take me that long, right? I mean, I had to explain it. But this method right here probably take me about 1.5 minutes maybe to do. So I would like to see that, demonstrate to me you know how to use either elimination or substitution for a system of 2 equations and 2 unknowns. Okay? Now in Cal 2, if any of y'all take Cal 2, we'll do some systems of equations that are larger. They're like 4 equations, 4 unknowns. And then I actually teach everyone, make sure everyone knows how to use their calculator to do it.
If we know how to do a matrix by hand, can we do it?
Well, yes, you could do this with the matrix by hand, but you don't really gain too much by doing that,
Yeah,
you know?
I just tried it.
Yeah. All right, we're almost done. I'm going to go ahead and come back in here, and I'm going to change my A to 3. And I'm going to change my B's to 2. So watch what happens. When that becomes 2, that's minus 2x. And then what does this become? 10. So this is going to become 10. I'm going to bring up that computer program again that I did the drawing where we were trying to get those to match up, right? And I can tell the computer to let A be 3 and B be 2, and let's see what happens. Do you trust that we got it? All right, so I can tell the computer to let A be 3, and then I can tell the computer to let B be 2. There it is. Nice, continuous function. See that? Okay. That's going to do it for continuity. I think we're... That's a great question, because a problem like this, I don't see that many real good applications for. Okay? We've pieced together a couple of functions in a cute way to make it continuous. I think a problem like this is important because it really brings together quite a few concepts. You're basically testing your brain's ability to put together a lot of ideas at one time, right? Which in the big picture, and this is a conversation we haven't had in this class, is, why are we actually in here taking calculus if you're going to be an engineering student or a computer science major, or even what, biology, right? And that's something that I toil with a lot. Academia versus true, like real world and stuff. And I think really it comes down to, like what I was talking about at the very beginning of class, work ethic. It comes down to training your brain to think a certain way, to process information a certain way, and demonstrate that you can learn material, especially like biology majors. This is more like, are you teachable? Can you learn information that's not necessarily easy to learn for everybody, right? If calculus was super easy, everyone would have no problems with it, right? So my brother is an engineer. He's an actual true engineer. He's applying his degree towards real life stuff. And I talk to him about this constantly. I always ask him what do I tell my students to make them feel like there's value in going to school? And his answer is always the same thing about being determined, being a problem solver. Okay, that's probably the biggest thing. This is a problem, right? Does it matter? Does it factor into your engineering degree or your biology degree? Is it going to help you become? No, but problem solving, that's what this is about. And if you're not a good problem solver, if you're one of those people where you see a problem and it's challenging and you just kind of wilt up and curl up in the fetal position and shiver, then you're not engineering material. You're not pre-med material. You can't be a doctor who goes into a room and is like, oh shit, find someone else to do that, you know?